Very similar to the last problem about concave mirror and converging lens. In this section, we're going to look at convex mirror and diverging lens. So this is the same problem, except I changed the converging to diverging and concave to convex. So again, we have two surfaces and there's two image formation. So the problem asks us to determine the location of the final image, the orientation, whether it is upright or inverted, and the magnification, which talks about the size. So we first look at this mirror first. We assume that it is a thin mirror so that we could use the thin mirror equation, and the magnification equations are valid. Sorry. So from a convex mirror, it is a diverging mirror, so the focal length should be less than 0. And the magnification works for both convex and concave mirror or lenses, so I'm not going to stress a bit about it. But the image distance, when it is greater than 0, then the image will form in front of the mirror. But if the image distance is less than 0, then the image will form behind the mirror. So after we apply the thin mirror equation, we have the image distance and we have the magnification. So we say the first image is diminished, virtual upright, and 11.1 centimeters to the right of the convex mirror. And we're trying to double confirm this result with a ray diagram. So we have the object here, and then we have the mirror here. So we first draw a parallel ray that goes with the focal point. And then we're gonna draw a focal ray which goes from the tips to the focal point. So this is the ray, and after it would be so this gray line is the guideline because the ray shouldn't be at the back of the mirror. So actually the first parallel ray, this ray, it should be virtual. And then it is gonna go parallel with the optical axis, and this ray, of course, it is also virtual. And by these two rays, we have formed an image. And then we're gonna connect the dots of the two image to find our central ray, which goes after this point. It would be a gray line that is the guideline, that when it touches the optical axis, this is called the center of curvature. What it means is that when we're extending this convex mirror with a whole circle, then the C would be the center of the whole circle. So we have the first image, and it makes sense with the conclusion we have made, since it is diminished, virtual, and upright. Then we're gonna look at the second refractive surface, which is the diverging lens. And since it is a diverging lens, the focal length would be less than 0. And we assume that it is a thin symmetrical lens, so we could use the thin lens equation as well as the magnification equation. The same thing goes with magnification, except for image distance this time. When it is greater than 0, then the image will form behind the lens. And if the image distance is less than 0, then the image will form in front of the lens. So after we apply the thin lens equation, we have the image distance, the second image distance. Oh, I forgot to mention. For the second image, we are using the first image as the new object. So this would be our new object. And then we have the image distance, we have the magnification. We could conclude that the second image is diminished, virtual, upright, and 9.5 centimeters to the left of the lens. So when we're trying to do a ray diagram to confirm, since this image is too small, we are gonna enlarge it with this ray diagram. So we have this as the new object, and we're gonna draw a parallel ray to the diverging lens, and this would diverge to our first focal point. And then when we're trying to draw the focal ray, since we have used this focal point, we're gonna use the other focal point. So we're drawing this ray with a guidelines, and then it would refracted parallel. And actually this should be virtual, and the actual refracted ray should be here. the same thing goes with the parallel ray. The refracted ray should be here, and the ray we're trying to draw with lining up the image should be virtual. So with the two rays, the parallel ray and the focal ray, we have formed the first image. Oh, sorry, we have formed the second image. And when we're trying to connect the two dots, we should form a central ray that passes through this point. But it is obvious that this diagram doesn't pass through this point, since I think there's some mistakes when I draw this, but diagram is not proportional. But in theory, these 3 points should be collinear when we're trying to draw a central ray. So when we're trying to compare the overall magnification, and we have to compare with the result, and it is diminished, virtual, and upright. Yeah, so everything makes sense. And we're trying to compare the overall magnification. We compare the height of the image. We're looking at the H1, we're looking at the H2, and we're looking at the H3. So again, we use two magnification equations to give us the last magnification equations here. And then we substitute the value, we have this equation. And we're trying to think if this thing makes sense. But we could first draw the conclusion that the final image is diminished. So we're trying to figure out if it is diminished. So we look at the first ray diagram. This is the original object. It is diminished after the first image formation. And we're looking at the second image, the second ray diagram. This is the first image, this is the second image. So everything is diminished. So the first one is checked. The second one, if it is the same orientation, we look at the first ray diagram. This is pointing up, this is also pointing up. But the question didn't specify that the object is pointing up. It's just say it is a point source. So we could not, and for the second ray diagram, it is pointing up. So we could not say that the image is upright to the first object, but we could say it has the same orientation. So the second sentence is also checked. The third sentence is kind of tricky. What I'm saying is to specifically locate the image compared to the first object. When we look at the second ray diagram, everything about the second image could only be found with the lens. So this image distance is 9.5 centimeters. And then we're trying to find this distance towards this distance where there's an object here. And this could be found here. The object here and the lens here, the distance is 50 centimeters. So we're just adding up 50 and 9.5 centimeters. Sorry, we're subtracting. And this shouldn't be 16.4. This should be 9.5. And this would not be 33.6. This would be 40.5 centimeters to the right. So after I subtract these two values, I have the third sentence to be checked. And that concludes the convex mirror and diverging lens.